Good afternoon, everyone. Really impressed at the sellout. I don't think we changed the menu from last time, so it can't be just the food here. Hi, my name is Shankar. I'm the Dean of the College of Engineering, at least for now. I'm stepping down July 1, but so I must say it's really a great pleasure to welcome you to now the 7th annual Ernest S. Kuh Distinguished Lecture series. And so wonderful to say 7th year, because I really remember when Bettine and Ernie first came and started talking about this lecture series and how Ernie had, and the two, Ernie and Bettine, had endowed a similar series at the University of Michigan. And then, I really remember that conversation. He said he wanted this to be a place where he had leaders in academia, leaders in industry, and leaders with an international bent sort of come and speak to the college community. And ever since that time, the Kuh Lecture brings an outstanding leader in technology and engineering to the campus. And the very first one, of course, was the Intel co-founder, Andy Grove. And it has been followed, I must say, by a very wonderful list of leaders, eminent leaders. So we continue that tradition of excellence today with the 2018 Kuh lecturer, Xiang Zhang, who's out here, you'll see in a second. Xiang, it should be noted, already has this title of Ernest S. Kuh because he holds the Ernest S. Kuh Endowed Chair in Engineering. So we are particularly proud to have him here, the Ernest S. Kuh professor delivering the Ernest S. Kuh Distinguished Lecture. So the lecture series, of course, was endowed through the generosity of Ernie and Bettine, who have truly been exceptional citizens of our College of Engineering. Ernie was a professor of ECS and a trailblazer in the design of integrated circuits and systems. And beyond his research, he was also the dean of our college and a national leader in engineering education. It has been a big loss, and even that seems really recent, when we lost Ernie in 2015. But, I'm very pleased now that we have Bettine in the audience. Let me single her out. There's Bettine, and Ted Kuh is the older son. Anthony, of course, is doing national service at the National Science Foundation, and Ted told me he was running a panel, otherwise he'd be here, but his wife is here, and Bettine's sister is, Susan, is here as well. The other members of the family, sorry, I won't introduce every one of you. But, Bettine, this wonderful annual lecture is really a lasting addition to Ernie's outstanding legacy at Berkeley. Now I'd like to invite Ted Kuh, and let me just say a little bit about Ted also. Ted, of course, is a Cal alum and also a graduate of the Haas School of Business. And most recently, he's been very active between the two colleges, the Haas School of Business and the College of Engineering, in launching a new sort of dual major program called MET. Management, Entrepreneurship, and Technology. It's sort of 2 degrees in 4 years for those who are not faint of heart. And he's been a trustee and one of the founders of this program. But I'd like him to invite him to the stage to deliver some remarks on behalf of the family. Ted.
Thank you, Shankar. Good afternoon and welcome to all. I will start by saying that I was not smart enough to get into the College of Engineering, so I had to go to the Haas School, which was still a fine school. We are extraordinarily honored to have Professor Xiang Zhang here as our 7th distinguished lecturer. He is incredibly accomplished in research, in teaching, and soon to be in administration. And my brother, who has never really profuse with accolades, said to me, he's a real rock star in his field. So I think we're truly grateful that you are here. I just wanted to say a few words about my late father and why he and my mother did establish this distinguished lecture series. For my father, Cal was really his second home. For almost 60 years, he was a professor and professor emeritus in electrical engineering and computer science. And he really enjoyed every aspect of his life here at Cal, certainly collaborating with wonderful colleagues, doing his research in integrated circuits and computer-aided design, and then also serving in the administration. But I think what he really enjoyed most was teaching and mentoring students. And during his career, he had the privilege of teaching 4,000 undergraduate students and 40 PhD students. So in 2011, my parents decided to establish the Distinguished Lecture Series because they wanted to give back to the Cal community for all that they had received during their lifetime. And it was appreciation that they wanted to show and provide for the Cal community to learn from true leaders in both industry and academia. So my brother, who unfortunately could not be here today, and I do want to acknowledge my mother, who has been a pillar throughout our entire life. And Joan is his representative. And then we also wanted to thank and acknowledge Dean Sastry, who all of you probably know is stepping down after 10 years as a dean. Certainly his contribution and leadership at the College of Engineering has been immense. So thank you, Shankar. So with that, I think Shankar is going to formally introduce Professor.
Thank you, Ted. We're delighted to welcome members of our Dean Society and to also acknowledge the fact that your support for the college and the students, all of whom you see, the enthusiastic, bright, shining faces in this audience, has really been critical. You know, all of the 10 years I've been dean have been times of budgetary duress, and it's your support that really has helped the college weather this and, in fact, thrive in the midst of these challenging budgetary times. So thank you very much. Thank you to all of you Dean Society members. And this year's Kuh Lecture is co-hosted by the Berkeley Student Chapter of ASME, the American Society of Mechanical Engineers. And our thanks go to ASME for their help in the preparations for this lecture. Thank you, Student Chapter of ASME. Where are you? The guys in the shirt. They have Berkeley Engineering polo shirts to show for their precious possessions, not sold. So let me tell you a little bit about Xiang. So much research that comes out of university labs influences our society, but it's particularly exciting when the work also manages to capture the public's imagination. This is the case with the research done by our rock star, I'm told, Xiang Zhang. Professor Zhang is one of the world's preeminent scientists working with metamaterials. These are a class of materials that possess characteristics not found in nature. They are rule breakers. So Xiang and his lab have shown that they can overcome barriers and limitations previously set forth in physics and that had threatened to limit the continuation of Moore's law. Professor Zhang's research has opened the doors to imaging resolution and optics that had been previously considered unattainable, including the invisibility cloaks that bend life backwards, and which you've undoubtedly seen in the Harry Potter films, but he'll tell you how they really work today. His work on cloaking metamaterials has been featured by many prominent media outlets, and the research has been selected by Time magazine as one of the top 10 discoveries of the year, 50 best inventions of the year, as well as Discover magazine's top 100 science stories. Of course, Zhang has also been well recognized by his academic peers. He's published hundreds of papers in peer-reviewed journals, Science, Nature, and of course the usual set of journals. It's unusual to have as many publications in Science and Nature in a College of Engineering. He's been elected to the US National Academy of Engineering, Academia Sinica, the National Academy of the Republic of China. He's a fellow of 5 scientific societies, including American Association for Advancement of Science and ASME, of course. Professor Zhang first came to Berkeley as a graduate student, earning his PhD with Professor Grigoropoulos, I think, in 1996. He held faculty positions at Penn State and UCLA before returning to Berkeley Engineering as a faculty member in 2004. He has served with distinction at Berkeley. I should say he's serving with distinction at Berkeley. It's not a past tense here. He is the director of the NSF Nanoscale Science and Engineering Center, and formerly up on the Hill, he was the director of the Material Science Division at LBL. It comes as little surprise that his talents and leadership are recognized around the world. This past December, the University of Hong Kong named Professor Zhang as its 16th Vice Chancellor and President. The University of Hong Kong is among the oldest and most prestigious universities in Asia, so this is clearly a true honor. We are extremely proud of Professor Zhang and very grateful that in this says last semester, but at least last semester for now, at Berkeley, we are really proud of everything you are doing and continue to do. So without further ado, please welcome Xiang.
Yeah. Thank you, Shankar. And it's my great honor to be here today. Berkeley has been my home for many years. Especially, I think, today I feel I'm double honored. I'm Ernest Kuh Endowed Chair, holding for last maybe 10 years. And also today I have the other honor to give such a lecture in his name. And I'd like to take this opportunity to thank the College of Engineering, Dean Shankar Sastry, Department of Mechanical Engineering, and the campus has been really wonderful support for my work, for my life, and my lab here. So all the work I present here, essentially without those support, it's impossible. And also I'd like to thank the people, especially the student postdocs, my staff who work with me over years here. And without their work, essentially, this is also impossible. Let me begin my talk, with a picture of Ernie and Bertine, where Ernie, to me, actually, they're already, our dean speak highly about Ernie's scholarship achievement. But to me, actually, he's a great mentor. When I joined Berkeley 14 years ago, and when I was given this chair, I had the chance to meet with Ernie, and also we had in his office, he was retired at the time already, and we talk about research, life, and so on. And give me so many great advices, and also sometimes with the jokes as well. So I've been really benefit from his great wisdom. So today I'd like to share with you some of the work we have been working at Berkeley, especially so-called creating materials that do not exist in nature. Of course, we do not create the materials from the air. We use nature materials, but we build something totally different. So 3 examples I'm going to talk about: selective refraction, superlens, and cloaking. So I will give a very brief introduction. What is metamaterial? Then I will talk about some very unique physics associated with this artificial composite materials. That is optical magnetism, and that leads to selective refraction. And one of the, or 2 of the major examples of such a unique material is, one of them is that you can use that to build a lens that can see things much smaller and below so-called diffraction limit. On the other hand, since you can see, for example, you can use this material to hide it, so-called invisibility cloak. So I will talk these 2 extreme of examples, and hopefully that gives you a sense of what the possibilities these materials can offer. So What is metamaterial? We all know that, and I was told this is a more general audience public lecture, so I will try to make as generous as possible. We all know that materials are made by atoms and molecules, right? And specifically, if we take a piece of silicon or gallium arsenide, these are the basic material we use for making computer chips. We know that any of the nature materials, they have few very intrinsic attributes. First of all, those atoms, we only have actually 100 plus types of atoms in periodic table. That's what nature offers us. And Berkeley, I think we own about 13, right? 13 elements. Is that 13 or 12? And discoveries here, so we are really proud of almost 10%. But however, if there is a philosopher sits in the audience and he or she will wonder, well, why we are limited by 100 plus type of elements in the nature? Why can we create something 200 times, 1,000 times? Okay, yes, that's limited by the nature. But if we think about, if we enlarge these atoms in bigger scale, okay, and making these atoms, each individual atom is much bigger, let's say, become nanoparticles, which contains millions or billions of real atoms. But we call it artificial atoms or meta-atoms. Meta in Greek means go beyond ordinary. So this name actually was created by a DARPA manager, not by academics, so-called meta-materials. Means materials go beyond ordinary. So these are the atoms can be as small as few nanometers, or as big as centimeters, or in seismic waves, it can be a building. This building can be considered as a single atom. Okay, but anyhow, so these essentially are composite materials where it can interact with certain waves, such as optical wave, acoustic wave, or elastic waves. And one of the things is by building these artificial atoms, we can assign specific properties to each of these elements. Therefore, we can engineer the physical property wide go beyond so-called 100 elements in the periodic table. Of course, this is only limited by your imagination because this is where the entities you can engineer. For example, you can find a way to circulating a current on top of that. Then you have a magnetic moment, right? And you can create magnetic artificial magnetism, which I will talk about in the next few slides. So the other thing is you can put this into an elastic medium, like rubbers. You can stretch them 100% of the lattice constants change. While in the real crystal, if you take any silicon or something, if you try to press it, few percent is already very large. So by tuning that, actually the large distance between the atoms, you can tune the property very dramatic way. Also, you can make a compound like sodium chloride as well. One of the things actually is also not only we are bounded by a number of atoms where we have a choice in the periodic table, but also if they form a solids or crystal, they also have a given set of symmetries you can play with. For example, this only have a certain translational or rotational symmetry you can play with. By doing an artificial composite, you can do much more symmetries you want. So what's wrong with our nature? Well, if we look at the electromagnetic property, which means that materials respond to the electromagnetic excitations or microwaves or optical waves. I won't go to details of this Maxwell equation, but this is a quadrant I want to show you. This actually has a 4 quadrants. Horizontal axis epsilon represent the electrical response of the material to the external field excitation. Y-axis is the magnetic response. Okay, so for external excitation, electrical, magnetic, they respond differently. Now in this quadrant, epsilon mu are both large, positive, which is most of glass, water, those are so-called dielectric states here. Okay, then over here you have epsilon, electric response is elective, but mu is positive. That is metals, ionic crystals, for example. And over here, it is actually epsilon larger than 0 and mu less than 0, which exists of certain low-frequency magnetic materials. The nature, however, gives us an imbalance where this quadrant is missing, especially at high frequency, at optical frequency, where the materials simultaneously has epsilon or mu, lective, or not exist. So nature gives us 3 quadrants, but missing one. So Mr. Vyslago, a Russian theoretician physicist in 1968, speculating, what if we have this both simultaneously, the epsilon mu, electrical magnetic property, goes to lective? Well, he said, well, if you look at the high school Snell's law, which dictates how the light bends from one media to the other. Let's say this is air, this is glass. We know that when the light travels from the air to the glass, it will bend it in an angle, right? So we know that the energy flows this way, momentum flows this way. But he actually speculating, what if actually one of the indexes, whether air or glass, become lective? Now, by the way, all the later materials index, optical index are positive and larger than 1. He said, well, what if we have lective values? Then he found out actually the energy flows in opposite angle instead of on the other side, on the same side of the incident angle, but momentum flow backwards. And this is very interesting because momentum flow backwards means that actually there is a conservation to be conserved along the tangential direction. But there is a physics reason why they have to move backwards. And we will show that in an experiment. So this is actually very interesting. But at the time of 1968, there isn't any continuing work because nobody knows how to construct such materials. And it is not existing in nature. And until 2008, when the first optical metamaterials shows selective index in a bulk property here at Berkeley, we actually did experiment in Echeverry Hall. And Science Reporter actually draw this. This is not exactly right, by the way, but capture general idea. If you have a straw in the water, it looks broken, but it's not broken. It should be continuous straw. The reason you look at it's broken is because of there's a optical phenomena called refraction. The light bends from one media to the other media, from air to water. Okay, that's why it looks. But he articulating that if this is water contains selective optical index, the straw will bend it this way. It's not exactly right, but generally, capture sort of the contrast of the ideas. Okay. But more accurately, my student Jason Valentine, he's now professor at Vanderbilt. He actually produced this cartoon. That means actually in a pond, we know that if you have a fish and a person observed the fish in the water, right? And now if we change the pond water into a lective index media, or refraction index is selective, what this person will see is a fish flowing above the water. And upside down, the fin actually is down now instead of up. Okay. So that is this is correct, I verified. At least in theory, okay. At least in theory. I couldn't create the water in lective way. But the whole field actually starts from a brilliant proposal by a British scientist, Sir John Penry, in a 2000 PRL paper. He proposed that, by the way, we all know that nature materials has magnetic materials, which, magnets, right? Magnets, we use that for information storage, for your hard disk, and so on. But he said, well, what if the materials of property doesn't have a magnetic response? The parent material, let's say take a piece of aluminum or gold, but if you structure in such a way, in a certain geometry, that gives you collectively magnetic activity. And that is very striking. It's like a parent doesn't have this skill, but son is actually expert on that. So this is actually through a geometric structuring, and you end up with this very interesting artificial or collective magnetic response. And this was actually a very, very interesting development. And combining now, if you drive the magnetic response at from the non-magnetic materials, then combining the epsilon, which is the electric response, this we know very well. You chop the metal, become porous. You can shift their plasma frequency from UV to visible to microwave. And if you combine mu, magnetic property, epsilon property, both simultaneously lective, you end up with a piece of composite like this. You can make a lens out of it. And furthermore, Mr. Penry pointed out, this lens is very special. It can imaging things at a very small scale and below so-called diffraction limit. Okay. In fact, this is a cartoon I draw when I at the UCLA, and I was a young professor, and I saw this paper. I said, well, gee, this is opportunity. We do some experiment. So we wrote a proposal in 2000, only a few months after this published, and we tried to beat the so-called Muri program. It's one of the Department of Defense basic research program, and we got it, and we start, last 15 years or 18 years of research on this topic. So if this is true, can be realized, the optical index can be elective. And there's many things could be possible. For example, you can imaging things way below diffraction limit, and that is at the nanoscale. So that is very important for biology. And also, you can use the same way to develop nanolithography. You can print the circuits at a very small scale. And there's a group actually in London are actively pursue high frequency MRI. In fact, actually using this very high frequency magnetic field, you can do a lot of imaging stuff over there for medical imaging. And also, of course, for photonic circuits, you can scale down much smaller scale and biosensing. So first, actually, a metamaterial with selective index are produced at UC San Diego in the microwave range. So these atoms, these rings, are much bigger. It's about centimeter size, 1.5 centimeter size, 1.5 centimeter in size. So these are big atoms, big atoms. But for microwave, these are much smaller than microwave. I believe that in this case, the microwave wavelength is about maybe 10 centimeter. So for the wave propagating through this media, it's a vacuum media approximately. So they produce actually both epsilon mu smaller than 0. But then soon people, this is a very big milestone experiment, but people still arguing that in this frequency microwave, and you do have later materials, both epsilon mu are elective, so you don't need this. But nevertheless, I think this is a great, great achievement. The question is, in higher frequency, optical frequency, can we have that? The problem with optical frequency is n squared, the index of refraction is equal to epsilon permittivity times permeability, electrical magnetic, right? This we all know in the classical textbook. But if you move up the optical frequency, where all the later materials do not exist, display the magnetic response, okay? Especially after a few hundred gigahertz. Therefore, we always take mu equal to 1. And optical engineers always with one handle, which is epsilon, the electrical property, because there is no magnetic property in optical frequency. The reason is that optical magnetic actually activity or response of the materials are raised up from the magnetic dipoles. In contrast with the electric response are from the electrons largely. It's a monopole. And I always use this example. Dipoles, they cannot sustain themselves. They have to form a domain or group. And it's like a division of soldiers. And they are lined up in the field. You ask the division of soldiers, a few thousand people, move back and forth at very high speed. That's very hard. Now, if you have gorillas like electrons or individual monopoles, they can move back and forth very fast. That's why metal are shiny, right? So the magnetic actually activity at very high frequency do not exist after above a few hundred gigahertz. That is the reason, because they have to move together thousands of dipoles, millions of dipoles, so-called magnetic domains, flip back and forth. That's hard. So usually later materials magnetic activities fade away above a few hundred gigahertz. What Sir John Penry actually proposed is, well, let's take some non-magnetic materials such as aluminum or gold. We structure them into a so-called split ring structure where they have two concentric rings. This is top view, where they have two split 180 degree. That's for phase actually coupling, where these two concentric rings, when you excite with the external magnetic field, you will generate a loop current. This is induction current in the metal. And they are capacitively coupled. So these two split gives you that 180 degree difference. Therefore, they can be capacitively coupled. Therefore, when you have an inductance, a capacitance, you know what happened. Many electrical engineer here, right? You have RC circuit that gives off give rise of the resonance if you drive to the right frequency for the geometry. And that's exactly happened here. So if you drive that to a certain frequency, at microwave or even higher, and the magnetic response indeed actually shows up, So this is very interesting, though John Penry showed that in this paper where the microwave version of that can be realized. The question is we ask ourselves at the time whether we can push up to the optical frequency. In this case, it's the far infrared or terahertz, where the magnetic activity for all nature materials disappear. So we indeed actually using this split ring structure, and this is sort of microfabrication. Each of the atoms is about 26 micron in size. It's still very big. It's not small. But for terahertz wave of 100 micron, this is a continuum medium or affecting medium. You can treat it. Therefore, we observe very strong magnetic response of this a single layer of atoms, of artificial atoms, operate at terahertz. So as you can see, you can tune this by tuning the geometry as well. And this is in collaboration with Bassoff and Smith in UCLSD and Penry in Imperial College. So the question is that, can we move up to truly optical frequency? And yet it is not a single layer of atoms, rather, because we know that we have a crystal that's a three-dimensional. So we want to create a bulk lective index materials. And the way we did is actually, again, we take a nature materials, we build it into a composite. The way we do that, we do first the stripes. These stripes are made by dielectrics and metals, dielectric metals. These two colors represent two different materials. We stack them up in stripes. The optic wave coming from the bottom and with the magnetic field actually parallel to the stripe. Okay? That will excite the magnetic resonance. Look at here, there's a cross-section of this stripe where you have inductance in the metal and capacitance across the dielectric. And so you have these little LC circuits operate at a very high frequency, hopefully at optical frequency. That gives rise of really interesting magnetic dispersion. And this bottom curve shows the frequency and the phase advance, or K. This is dispersion where two magnetic modes are show up here. In between, there's a magnetic band gap, this material. It means that any electromagnetic wave or optic wave, if their frequency falling into this shaded area, cannot travel, which in the other words, their mu is selective. The magnetic permeability is selective over here. Okay, they decay in this frequency. So we take the other stripe, which is 90-degree perpendicular, a little bit different, thinner structure, and for the same optic beam coming from the bottom, now this responds to the electrical field, which is parallel to this. And this is actually effectively is a diluting metal because each of the layer thickness is much smaller than wavelengths of concern. So for optic wave, you view this as affecting media. And for diluting metal, you can shift the plasma frequency to a longer or shorter, a smaller frequency that matches with the magnetic magnetic band here. Therefore, below this plasma frequency, epsilon, the electrical permittivity is selective. So we have these two shaded areas, epsilon and mu, respectively, are selective. Now, what we are looking for is they are simultaneously selective in this overlap frequency of the range. When you have both of these going to selective, and this optical index of refraction should go to selective. So this is exactly happened when we combine these two structures together. We have so-called fishnet structure. It's like fishnet, right? And indeed, actually, you see now individually these two structures prevent optic wave are propagating through this structure. But if you combine them together, they allow actually wave propagate. So there's a mode actually exists in such optical band. But not only exist, but also if you look at their slope, it's selective slope. It means that energy travels this way, momentum travels the other way. They are opposite in 180-degree, opposite direction. So that is where the elective refraction about, because the elective index of refraction is about the phase index. So we decide to make this structure. This was made in the microlab here. Used to be in the, I think 2008, have we moved here? I think so, right? So, but in anyhow, either in Corey Hall clean room or here, that we deposit multi-layer of silver and magnesium fluoride. Each of layer is about 30, 50 nanometers. And then after many layers of deposition, this is a standard semiconductor fabrication. Then we use a cutting tool. This is a special cutting tool, so-called focused ion beam. It's like mechanical cutting, where this beam can be focused to 5 nanometers. And you come in and cut a square hole, like as a design. So this is a design. This is a fabricated structure. And this square hole, if you look at more carefully, each of the layers are metal dielectric, alternating, as you can see here. Now, if everything is right, designed by theory, this should give us a elective index of a refraction. If we shoot a beam from the bottom, they will refract in a elective angle. So we want to do a high school type of experiment to shape this into a wedge. This is a slab of material. We believe this should have elective index. Okay? We shape it into, we use the same actually cutting tool to shape it into a small angle. And by the way, we are so grateful for the micro nano fabrication facility here, that which is a wonderful facility, and I believe this also related with the Kuh's former students actually made contributions to this building. So we are very grateful. This enables us to measure the world's first actually elective index materials in a bulk media, where we make a prism. The index of refraction along the vertical direction should be elective, so we shoot the beam from the bottom. Now, then we watch it with a camera here. If they are refract on this side of the normal line, the dashed line is the normal line perpendicular to this. If this wave come out from this side, will be positive. If wave come out from the other side, will be elective. Okay, so we basically record where the spot is and determine. That is, basically all the high school kids probably do the same thing for refractive index measurement. So we measure how the spot moved as a control experiment. We just have a window here without the prism. As you can see, when we change the wavelengths, the spot doesn't change. It's just a vertical passing through. But with this prism, which we believe contains the elective index of refraction, this spot moves. And if we plot all the positions and convert that into a refraction index, refractive index, and this is a plot where this is the index of refraction, this is the wavelength. Now, this material has a dispersion, therefore show the different index of refraction at different frequency or wavelengths or colors. As you can see, actually, at 1.7 micron, this index can be indeed -1, where what does that mean? It means that actually energy travels this way, momentum travels backward. But interestingly, not only we realize the elective index, but also at 1.5 micron of the wavelengths, which is a telecommunication wavelength, by the way. That's all our internet are operated. And this index is a 0. What does a 0 mean? It means that the optic wave hopping through a finite distance doesn't need actually a time in terms of phase, Now, the phase speed in this case, in this wavelength, is infinite. Maybe some students say, well, wait a minute. Einstein say the light speed is a limit, but this is the phase speed is not energy travel speed. So there is a difference, okay? The phase speed, essentially, when you throw a stone in the pond, the ripples propagate out. That's the phase front. And that is equivalent to that. And in addition, there's an interesting phenomenon we observed here, where the index actually is not 1. All the later materials should be above 1 because of air and the vacuum are defined by 1. Nothing below that. But we observe that something at 0.5 or 0.7, that's even faster than what travels in vacuum. So that is also very interesting. But anyhow, I want to show this video and how that works. So wave coming from the bottom as a plane wave and travels through this prism. And when they actually at 1.2 micron is a positive index, but less than 1, by the way. So the wavefront actually is in the left side of the white line, which is the normal line of the exit plane. And if you look at the electric field and magnetic field, they travel indeed from bottom up. You look at the wavefront is going up. And therefore, the energy and momentum does travels in the same direction from bottom to the top. Now, if we switch to longer wavelengths, where index of refraction of these media are elective, and what we see here, the wavefront skirt much towards the other side, and we indeed have the wavefront become elective. And if you look at the wavefront travels in the magnified structures here, and we see the wavefront, the phase actually travels backwards, while energy travel from bottom to up, the phase travels backward. Indeed, this verifies they travels, energy and momentum travels opposite direction. So you may say, well, what is this useful? Well, I'm going to show you quickly the two examples. One is actually this indeed can be the diffraction limit if everything works right. So this is a cartoon I already showed, and we haven't reached the DNA level yet. It takes much longer time, but we have actually a very long project actually here, next 4 or 5 years, funded by Moore Foundation to pursue this so-called super microscope. So what's the problem of diffraction limit? Well, the resolution of optical lenses, including our eye, has a certain limit. So Mr. Ernest S in 18th century, he pointed out when you use a lens to image object, here, whether your eye or your camera here, okay, when you image two dots together, you bring these two dots closer and closer. At a certain point, their image merge together. Okay, you cannot resolve them successfully. And that is inherent limitation, so-called diffraction limit. And typically, this distance between the two dots are about half of the wavelengths. Now, if some of us biologists here say, wait a minute, we can resolve 30 nanometer today, and we can turn two molecules next to each other, one green and one red at a different time. But physics here says at the same time, simultaneously. You have to resolve them simultaneously. Of course, if you resolve them at different time, that's possible. So what's wrong with the positive index? All the nature material made, whether glass or our eyeball, which largely is water in the eye, right? So I want to go to the mathematics. Basically, if the index is positive, epsilon mu are positive, where you have, when you do an imaging, essentially it's a Fourier transfer process. When I look at you, because the light shining on you and scatter off from your face, and my eyes is like lens capture your image and on the backside of the eye, then I say, oh, I see you. So there are two things actually, two type of information I can see. One is so-called propagating wave, where the k vector are small. It means that corresponds something pretty big on your face, your eyeball, your nose, and which I can see. Now, there are some biological cells which if I use a microscope, I can see. But however, the things inside of cell, let's say proteins, 10 nanometers or even smaller, I cannot see because those are corresponding, very small feature size corresponding very high k vector. That forces the kz, because these are conservation of k over compared with omega over c. So kz become imaginary if this kx, ky is too big. That is, if you plug in this mathematically into the propagating wave, these two imaginary parts become negative sign. It means this wave amplitude is decaying in space. And typically, these are so-called evanescence wave. You do not collect them. So imaging with a positive lens is always imperfect. You only collect maybe 98%, 99%, but there's 1% of details you don't capture. That is beyond diffraction limit. Okay? And that is why there is actually a minimum we can resolve, that is fraction of wavelengths. But Mr. Penry actually in this theory paper pointed out that if you have piece of media, at that time we don't have that yet in 2000. And if index is selective, you can excite this decaying wave or lost treasure of the information, very fine details. You can excite actually surface resonance. In that condition, you may actually reconstruct the amplitude of such a wave. And of course, this enhancement or amplification will decay again in the positive space, in vacuum or in air. But before that decay too much, you can collect them in the image plane. So you can actually recover or capture those lost treasures. But this doesn't violate energy conservation. I will probably, if I have time, I can answer some questions. But in any way, that through some mathematical operations, he showed that this is indeed possible. And soon, actually, my student Nick Fan used a simulation indeed to show you can resolve 2 nanowires space at 60 or 80 nanometers, and you can have their image captured. theoretically, this was a calculation. And experiment took us quite a bit of time, and this was maybe one of the first papers I published after I moved to Berkeley. And essentially, we have a nanoscopic object, which are nanowires, or you can use a FIB, focused ion beam, to write a nano, which with a width of 40, 50 nanometers width. And through a silver slab, their epsilon can be elective at UV frequency. Therefore, this is a poor man's superlens because in 2003, 2004, we don't have elective index of materials until later on. So we use actually, but the physics shows the same if they are at electrostatic limit. Therefore, we use this photoresist to record the image on the other side. So think about this blue silver slab as a lens, so-called Pullman's superlens. It's not elective index, but show the same effect because epsilon is elective, except mu is not. If you operate at the near field or at the electrostatic limit, that the physics is the same. So we capture, indeed, we resolve the 60 nanometer nanowires. And Nick's group, Nick is now full professor at MIT, and his group actually further pushed down to 30 nanometer wires. As you can see, this is the image at his group. And later on, we project this image even to the far field, which I'm not going to go detail due to time. But in any way, the ideal is, can you make a scope, microscope, now we can call nanoscope, indeed go beyond much smaller than diffraction limit. So this is a project we are ongoing right now, and actually we are in phase 2 funded by Moore Foundation. And this, we just begin the phase 2 here at Berkeley. And let me show you the other interesting application, which is everybody knows that Harry Potter's story. Though I have to say, it still takes a long time to make practical devices, but we're getting, a step by step. So I borrow a few slides from my collaborator, John Penry, from Imperial College, where this is very interesting for Peter Pan. He likes Peter Pan. Now, Peter Pan is here, and you can make Peter Pan disappear, just paint it black. But black is not invisible because you see the shadows, right? So that's not good. What really he views that if you can make 70%, 75%, 25% of the image lost, and 50% and totally lost this. So you see his body is transparent. Okay. That would be cool if he can, wear something, a cloak. So what this requires in physics, it requires actually a blue color cloak here that has a very special property. Let's say the light travels from left to the right, and like water, passing through a rock here. We want to put things, want to hide in the orange area. Okay, so this is the area to hide your object, and this is a cloak. And this travels in the air. Now the light travels around it, usually will bring the different phases. Therefore, by look at the phase difference, you will see the fringes, and you say, oh, I see you. Or I see ripples of the water after rock. I see there's something, disruptive there. But the idea is to make this flow of light or water seamlessly, where when they come out, they are the same phase as travel outside in the air. So then, for the downstream observer, if you look at that water or light field, nothing happened. Okay, it's like stream of the light. So you have to make light travels here faster because they travels larger distance compared with straight line, right? How you make it faster? Remember, when the index is less than 1, less than air, you make it faster. So that's why you need metamaterials to do these tricks. And this is a simulation to show after the plane wave comes in, plane wave come out, and everything reconstructed. For the downstream observer, nothing happened. They see, oh, there's nothing there. So in this theoretical paper, this is even earlier, that Penry and his student proposed that I want to go to the theory where how you construct such a cloak. So he gave a theoretical blueprint for how you construct such a cloak. Essentially, you have to renormalize the uniform space in air or in water, that you can dope the space, make the light making curved trajectory. Due to the time, I will go faster. So again, it's very hard to make such a cloak. The first cloak was made by Dave Smith in Duke, where they make a microwave cloak. Because microwave is bigger, as I say, well, all the atoms are centimeter in size. You can tweak things. You even do machinings, actually. So the idea is to make the mu along the tangential direction is constant, but along the radial direction is almost linear dependence, less than 1. So that's the idea. Okay. So as you can see, they indeed made the cloak, and experiment shows that it's pretty good, but there's a little shadows cast still. This is, experiment imperfection. We think about how we make it optically invisible. So one of the scheme we use is a carpet cloak. Imagine this is a carpet. Somehow it didn't store very well. There's a bump on the carpet. So you can see it. The bump is pretty big. You can see it. The question is, can we hide it? Well, you can construct something above that and hide it. So the idea is to transform mathematically a physical space into a virtual space, which to the observer is a flat. It's a flat. You don't see the carpet bump. Okay. So mathematically, we can describe a cloak design in such a way their permittivity, epsilon, can be varied in the space. Therefore, when the light comes in, they will route it around this hidden area, these bumps, and come out as if they are reflected from a flat mirror or flat surface. So you make the bump disappear. And this is indeed possible. So we start the experiment testing this idea. We use the optical waveguide. This is quite common so-called SOI wafer silicon insulator, where it's a guided wave, and we drill nanoscopic holes, many holes, but we vary the hole distance by this mathematical design. Therefore, this rectangular is a cloak. This green area is the things you want to hide. Put it here. Okay. Now the whole thing is quite small. It's a few microns. Well, this area is about 5 microns, but this area probably is about 50, 100 microns. So this is a cloak we fabricate again in the microfabrication facility here. And this is more zoom in, where the cloak shows this is where area you want to hide things. Very small at the time. We can only hide biological cells probably. But this is a demonstration of idea. And we drill holes, therefore we vary effective index or effective epsilon in the media. So the light comes in the waveguide, coming here, everything travels in the plane, in the 2-dimensional, and bounce off from here, and we observe here. Now, if there's a bump, this bump is a few microns, so if there's a bump, you will see the scattering. There's something there. That's how we see each other. But if we can hide it with this successfully with this cloak, then you will see as if reflected from a flat mirror. So this experiment indeed, so this is the mirror. If we shine light here, bounce off, you will see a nice Gaussian beam as if nothing happened. Now, if there is a bump here, which are larger than wavelengths, of course, you will see the scattering. That's why we experimentally can see, okay, there's something there. Now, if we put the cloak on this bump, okay, and when the light hits here, the cloak actually make the light rotate around as if that reflected light coming from a flat mirror, nothing there. Okay. But of course, this not only has to work at 45 degrees at any angles, because if I can see it from cannot see it from any angles, that's a cloak. So this video shows how the cloak works. If I have time to basically make. So when the light comes in, there's no cloak. You see the scatter of the light. There's a shadow cast. Observer will see, oh, there's something. Now when I turn on the cloak, everything emerged as a single beam, as if nothing happened. But maybe I move on to the next one. It's more interesting. Now, that cloak is very small. We made in Berkeley, but it's the first optical cloak. 5 or 6 years later, a group in Singapore makes much bigger. And in this case, actually, they try to cloak a fish. This is the, well, let me show you here. This is a tank of water. Inside, there's a hexagonal cloak here, okay? And there's a hole. The fish can get into the hole of the, you can view this as a cloak, and fish get into the hole. Now, there's a grass on behind it, and then observer in front of it. Now, if nothing happens, you will see nothing, and you see the background. Now, if fish get in there, it can make the fish disappear. Okay, so let me show you the video, which is published 2003. So there's a fish there already. You see the tails here, but it's hiding in that hole right now. They try to get the fish out. Now the head is out. And they try to, I think the hole is not too big, so they're somewhat stuck there, and they try to shake the water to get it out. I think finally it will be out. So now they flow outside. Right. So there is a possibility. But now if you look at this cloak, my son told me that this is not fun. If I want to hide myself, and he joked that he wants to rob the bank, he has to have a big cloak carry, and somebody can touch it. Of course, it's a big object. So the idea is, can you make a cloak? It's a skin cloak. It's like a mask, really very thin on your cover. And indeed, a few years later, that my student postdoc made this actually so-called skin cloak, very thin. It's about 80 nanometers. Essentially, and cover 3-dimensional object. And essentially, this is conformal as well. Now, you may say, well, besides this demonstration, what is useful? Well, if you think about, we can make something disappear. We can make something appear as well, if you do reversely. So actually, we are actively working on, for example, how we use this technology for so-called augmented reality. Most of you young students knows that virtual reality is the most for games, but augmented reality, there's a lot of positive. For example, train doctors with augmented reality where you can see through CT stored images, you can touch the surface and you see through 3-dimensional images automatically. So you can project a 3-dimensional image as well, and you use the cloaking to mask whatever over there, and you project a new image on top of that. With that, last slides, I want to specifically thank the endowment of the Ernest Kuh Chair, that because I wasn't funded by any other funding agency at the time, and we, my student and postdoc, we study some very fundamental issues of how we can break the time translation symmetry. So in this paper, published in 2012, independently, MIT group, Frank Wozek, also published, we published back-to-back independently, proposed so-called time crystal, where you can break the time symmetry, make a time condensate. We know that history is the river of time, and usually, even in quantum mechanics, we don't condensate time. It's E I omega t. T is always continuous. But in real crystal, as we know, the atom sits in periodically. Now we can make a time sits periodically as well. And this theory was actually realized by experiment by Maryland group in 5 years later. And I like to acknowledge all the students. This is older slides, but some of them already left. But these are former students contribute over last 10 or 15 years work here at Berkeley. And many of them are on faculty at various of university. Thank you. Yes.
Okay, we'd like to invite a few questions from the audience and give first preference to students. There are some microphones there.
Julia has a question.
How do you see?
Please name, major.
Maybe we'll wait for the audience to have questions.
Oh, Dave.
How do you see these metamaterials becoming, like, do you think we'll be able to scale them and mass produce them, and maybe everyone can have invisibility cloaks in the future, or do you think it'll be really difficult to make a lot of these in the future?
That's a great question. We haven't done that here at Berkeley, but one of my former postdoc, now in University of Colorado, he's a professor there. They are doing a roll-to-roll, actually. He showed one of the I saw the news that 10 feet actually of those materials. That is for different application actually. Metamaterials now, he started a company for radiative cooling, basically air conditioning without electricity. So I don't know the efficiency of that, but sounds pretty cool. And in principle, the metamaterial actually can do. So he showed experiment and manufacturing of that. In his lab, it's a 5-ton of machine and row to row to make those sheets of plastics with some particles inside, where they can do 10 degrees of cooling without electricity.
Hi, Professor John. I'm from Material Science Department. So I have a question about the evanescent wave. So you said that you put a superlens over there, and the evanescent wave gonna increase the magnitude. So where does the energy coming from?
Right, that's a great question. I don't have time to cover, but great question. Evanescence wave compared with the propagating wave. Propagating wave does carry the energy forward, okay, or backward if you depend on direction. Evanescence wave, you actually plug in that 2I cancel out. So they do not actually, if you look at it, it's oscillating field in the same phase. They don't even have a phase difference. So the field is oscillating field, doesn't propagate the energy. That's why you essentially use these two resonances on the surface, redistribute the field in the space. So, so therefore, you do not actually gain energy or lost energy. Rather, it's like you make everybody's salaries the same. Essentially, it's a redistribution of the energy essentially, because evanescence wave doesn't carry the energy flow.
Hi, Professor Xiang. I'm from Guru Group. So, and I have a question that from your presentation, it looks like the way you pursue the metamaterials, like the way you chase, you're increasing the frequency. And it looks like you're starting from long wavelengths and to the optical wavelengths. Right. And also you actually managed to fabricate the metamaterial in the optical frequency. Then the question comes, then, can you point out or one of your colleagues may be working on that, what would be the next thing for the metamaterials? Because the wavelengths-wise, optical wavelengths is already that highest. Then maybe there are some other field that we can explore. That's my question.
Yes, I think of course a lot of people now make a living in this field, so they have to find something to do. So one, I want to say that there's many applications right now. Even the scientific part hasn't really explored yet. For example, symmetry is one big deal here. We already showed there is a certain symmetries. Even Professor Fleming here is here that the chemistry try to make a molecular different symmetry. Mobius symmetry is very hard to make in moleculars, but here actually we can use this to show really the symmetry breaking and very interesting material properties that do not exist in or very hard to achieve in nature materials. So, but then applications, of course, there are various of, for example, there are a group across the Bay now in the other college across the Bay, and looking at scanners for the LIDAR, for example. We are also actively looking at that. So there are various of augmented reality is a big thing actually now. This gives you a possibility to look at, can you project your watch into a three-dimensional pictures, things like that. Yes. That's what my former postdoc, he's making actually this meters long plastic has specific particles there. They measured about 10 degree cooling down, actually, without the electricity.
So, Sean, this has been a fascinating afternoon here. And I wanted to say, some other friends of the college have endowed Wang and Wenqi, who endowed a sort of the Wives Center for Augmented Reality, actually in Corey Hall. So when you've had enough of Hong Kong, you know, we could use you to do some augmented reality.
I also need the augmented reality over there too.
So anyhow, this is a really
Thank you.
fascinating, sort of scope of your creativity here. So on behalf of the college, actually the students will present you with a small remembrance of today's event. It recognizes our deep appreciation for your commitment to engineering innovation. Thank you very much.
Thank you.
Go ahead and pose.
Thank you. Thank you. Thank you very much. Thank you.
Thank you also. We can also give you a polo shirt. Don't worry. Thank you also to our co-hosts, the American Society of Mechanical Engineering, and especially to Bettine and Ernie Kuh for making this outstanding forum possible. Thank you all for being with us today, and go Bears.
Thank you. Thank you very much.